Next problem is called Permutations II. If you're given a collection of numbers, nums that might contain duplicates, which is the important fact here, and we have to return all possible unique permutation in any order. So the final output cannot have duplicates. And here we are given the example 1, 1, 2, and here all are the all permutations without duplicates. And the constraints are pretty similar to the constraints that we have had inside the permutations problem, permutations 1. So to solve this problem, we will basically have the same modifications that we had from subsets 1 to subsets 2. So to bypass the duplicates, we will first sort the array, and then we will only, for the current position, let's say position 3, we will select the element if it's different than the previous element, so that we don't have, for example, 1 and 1. Or if it's the same, we will only select it at that position if the previous element has been also selected. So basically, all the elements, all the possible candidates, are dependent on the previous ones if they are of the same values, and we are only choosing them if the previous value has already been selected. Just as we had inside the permutation 1 problem, we will define our result, which will be a list of our permutation that we are generating. Then a slight modification, we will sort the arrays, so we can use the sort as the order of the array to bypass the duplicates. Next, we will call the helper function. It will again contain the set of candidates, which is our input array, as the first parameter. Next parameter will be the permutation that we are currently generating, which will be initially an empty list. Next, we will pass our result, to which we will be adding all the permutation that we are generating. And in this case, we are using an array of the same length as our input array, but of type Boolean, and this will represent if we have already selected an element or not. And we basically just return the result. Now for the helper function, we have it as basically as the same as the one that we had in the permutations 1. We will check if the current list, the current permutation that we have generated, is of the same length as the input array, in which case that means that we have reached the end of the recursion tree, the leaf node basically, and we have to add the current list to the final list of the permutations. Next, as we had before, we will traverse through all the candidates so that each candidate can be placed at position 1. And then we will check, just as we checked in the permutations 1, we will check if we have already added it. So if we have visited in the previous calls of the helper function, so that we don't choose it again. And then we will have basically 3 scenarios. This is the modification to the permutations 1. So it's either we are choosing the first element, in which case we cannot have duplicates, or the current element, it's not the same as the previous element, in which case we can just freely select it, or we have already selected element before, which is basically the same as our current element, is a duplicate. So in example 1, we will have 1 and 1, so we will select the second one only if the first one has already been selected in the previous calls of the helper functions. And then we will follow the same logic as we had for the permutation 1. We will add the current number to our permutation that we're currently generating. We will mark it as visited. Then we will call recursively the helper function. After we are done with that call, we are basically moving up from the recursion tree and going to another to the right children nodes. So we have to backtrack. We are removing the latest element that we have added before calling the helper function, and we also have to mark it as not visited. The space and time complexity are basically the same as in permutations 1. For the generation of the permutation, we have n factorial, and because we are copying over this array list that the current list that represents our current permutation that we're generating, we have multiplier n for each of those permutations. Now for the space complexity, because we are only passing the current list, which is of maximum of the size of the input array, we will have space complexity proportional to the linear and proportional to the size of the input array.